We're going to continue with thermodynamics today. We already defined some very simple thermochemical terms. We learned how to calculate heat transfer, and we discussed calorimetry. And your lab will focus on calorimetry later this week, where you will be determining caloric content of certain foods, probably potato chips, but if you have a junk food that you want to test other than nuts or peanuts, you are welcome to give it a try. Today we're going to learn a little bit about change in enthalpy. We'll learn how to interpret changes in enthalpy and also how to calculate values of delta H, the change in enthalpy. We'll learn how to do it two ways. And then later on in the chapter we'll focus on entropy and free energy. So we're going to pick up with the change in enthalpy. We already had indicated that the universe is divided into two parts, the system and the surroundings. This is a very simple video on system and surroundings. Let's take a look just at the beginning part.
Hello, welcome back to Thermo. Today we're going to take a look at what the system is and what the surroundings are for any chemical reaction that we're going to be doing.
So the system plus the surroundings together make up the universe. The system is what you are studying, typically the chemical reaction. The surroundings are everything outside it.
Class, understand that when we're doing a chemical reaction, whatever we're observing at that moment would be considered the system. And then everything else around that would be considered the surroundings. Again, when we're doing a chemical reaction, whatever we're observing at the moment, whatever we're testing, I guess, would be considered the system. Now, one way to classify chemical reactions simply is whether or not the energy change goes from the system to the surroundings, or gets lost by the system into the surroundings, or the energy goes from the surroundings into the system to actually cause the chemical reaction to happen. Now, let's identify what that is. So if the energy is going from the system to the surroundings, we say that the chemical reaction is exothermic. If the surroundings are donating energy into the system, providing energy into the system in order for the chemical reaction to go, we say that this is an endothermic reaction. Okay? Think about it like this. Like if I've got a pan on a stove and I'm cooking an egg on the pan, and the stove happens to be on. If the egg is the system, then everything else would be the surroundings. If you ask the question, if the egg is a system, is it endothermic or exothermic? Well, the egg is receiving energy from the fire that's being transferred, that energy is being transferred into the pan in order to cook the egg. It's also got the air around it, and the air gets hot around it as well because of the fire. And if that's the case, it's still endothermic. So again, if the egg is a system, the egg happens to be the system, then we say that this is an endothermic reaction. Now, let's ask the question. Of all the components that I've actually drawn over here on the little whiteboard, in what situation would it be exothermic? Well, the only possible way that could be would be if the fire ends up becoming the system. And if the fire is the system, then everything else would be surroundings because it's donating energy into the air, into the pan, into the egg, into the handle of the pan, into a hand that grabs the handle, okay, of the pan, and obviously it absorbs energy from all those different components. So again, if a fire is the system, then this is an exothermic reaction. And that's it. I'll see you in the next lecture.
All right, and so again, these terms were defined for you, system versus the surroundings. We know that the law of conservation of energy indicates that any heat given off by the system is transferred to the surroundings. You don't want to lose any heat. That will be important when we do our calorimetry experiment. So any heat lost by one is gained by the other. And shown here, you can see the system and the surroundings. So the system typically would be either the contents, that is the chemical reaction, or you could consider the flask part of the system as well. The surroundings are everything outside. When the system gains heat from the surroundings, it's an endothermic reaction. The surroundings will get cooler, and that's typically what you feel. For example, when you perspire or sweat, you're trying to cool the body, endothermic. Exothermic would be heat lost by the system and gained by the surroundings, and if you touch the flask, you would feel the heat being released, and so the surroundings get warmer in this case. You see this, for example, if you dilute acid. That is a highly exothermic reaction. If you feel the outside of the flask, you will feel the heat being released. In an endothermic reaction, if you felt the flask, you would feel the flask getting cooler and cooler. And we can take a look at that when we do the lab. In AP Chem, we do a heat warmer lab. We design heat warmers, and then we make them, and we try and figure out the best substance to use to generate a hand warmer versus a cold pack. For example, if you play sports, let's say you sprain your ankle on the sidelines, it doesn't look too bad. You might break the cold pack where you're just mixing water with a chemical and it gets cooler and cooler. That would be endothermic. Entropy we're going to talk about next time. This is a measure of disorder in a system. We'll talk about entropy, variable S, that is capital S, next time. Our focus today is going to be on enthalpy, variable capital H for enthalpy. There's an H in there. And this is a measure of the energy content of a system at constant pressure. And your unit's going to be in kilojoules per mole. We can't measure enthalpy directly, so instead we measure a change in enthalpy. Again, a measure of the heat change at constant pressure that accompanies any process. And what you're going to see here is that the change in enthalpy will be the difference in enthalpy between the reactants and the products, not the energy difference, but rather the enthalpy difference. And again, units, kilojoules or kilojoules per mole. I'll point the units out as we do several examples. We already mentioned exothermic reactions where heat or energy is released from the system to the surroundings. You find this with bond making, so typically your synthesis reactions. And let's diagram that out a little bit better because this is a very important concept. What you're going to see momentarily is that the change in enthalpy under standard conditions, 1 atmosphere of pressure for gases, 25 degrees Celsius as the temperature. This is not STP, a little bit different. That means standard conditions. The change in enthalpy for the reaction is going to be equal to, and I'm going to expand upon this formula, and that's why I'm writing it pretty elongated, is going to be the delta H of the products minus the delta H of the reactants. Products minus reactants. Just remember, you should always go pee-pee before you go running, because if you have to go to the bathroom while you're running and there's no bathroom in sight, that can be problematic. So products minus reactants. In an exothermic reaction, abbreviated EXO, delta H will be negative. That means that heat is released. In order to get a negative delta H, you will see that the delta H of the products must be less than the delta H of the reactants. For example, 3 minus 5 will give you a negative delta H. So in this case, heat is released. And typically, you will see this with synthesis reactions. Most synthesis reactions release heat, bond making, generating more complex compounds than what you started with. In an endothermic reaction, delta H will be positive, so product change in enthalpy will be greater than reactant change in enthalpy. In this case, heat is absorbed. And you typically see this in regard to decomposition reactions. It requires energy to break something up, so bond breaking. And what we're going to be doing is we're going to be calculating the change in enthalpy for a reaction two ways. And I think you'll be very successful with both methods. The other formula that is indicated in your notes, and we're not really going to get into it this year, but it's good to mention, is that change in enthalpy is equal to heat transfer over N, where N is moles. And typically it's moles of solute. I used to do a lab where this formula was required, but the kids had tremendous difficulty with it, and it really wasn't too exciting. They much prefer burning potato chips because for some reason there's always somebody who thinks that's just the coolest thing. Alright, so what we're going to do is calculate delta H of the reaction. Before we do that, there are a couple of things we want to make clear. We're first going to look at standard enthalpies of formation. And I want to make sure you're clear on the nomenclature here. So what we've got is the delta H of formation. That's the change in enthalpy. Again, H. F is for formation, and you will be forming 1 mole of substance, and the not sign there, it looks like a degree sign, indicates standard conditions. 1 atmosphere of pressure, temperature of 25 degrees Celsius. The reference point, the point at which everything begins, is for elements in their standard state or diatomic elements in their standard state. And you will see that their delta H of formation is always 0 kilojoules per mole. So calcium, sulfur, and Cr there indicates the state of matter. In this case, crystalline. Crystalline essentially means solid. So what's coming around now is a thermodynamic property sheet. We've got delta H's of formation. We've got some other information as well on these sheets, so you'll be using them over several days. And so everybody should have this table. And let's take a look at this table. I've got it under the document camera. And highlighted in orange here are some elements in their standard state: silver, delta H of formation of 0, aluminum, beryllium, bismuth. You will note I have highlighted in green bromine in the liquid state, its standard state, 0, calcium, 0, chlorine gas, diatomic element, 0. So elements in their standard state, or diatomic elements in their standard state, have delta H's of formation of 0 kilojoules per mole. And you will see here for delta H, the unit is kilojoules per mole. As I indicated to you already, the F indicates formation of 1 mole of product, and as a result, when you look at equations that illustrate the delta H of formation, you can have coefficients as fractions. It's probably the only time you will see coefficients left as fractions. For example, if I wanted to form 1 mole of water in the liquid state, I must do so through its elemental counterparts: hydrogen gas and oxygen gas. So on the left side you must have elements or diatomic elements, or you could have a polyatomic element like S8. And when you go to balance this, you can't change this coefficient because this must be a 1 if you're talking about the delta H of formation. And so in this instance, you've got a coefficient of 1/2 before the oxygen gas. I won't ask you to do that. I just want you to see that you can have coefficients that are fractions in this instance. If I look at this table, I can grab my delta H of formation. But look, water liquid, water gas. So I want it for the liquid, and so for the liquid, it's negative 285.830 kilojoules per mole. For every 1 mole of water that you form, 285.830 kilojoules of energy is released. Because it's negative, it's exothermic, which is predicted in most synthesis, not all, but most synthesis reactions. If I were doing this for water in the gaseous state, just be careful here, because some substances do exist in more than one state of matter, so make sure you consider that before you make a selection. And you would have the same in this instance. Now, if you were looking at delta H's of formation for these elements, they would be 0. And that's why I said in number 4, be careful of substances that exist in more than one phase. You'll see it here. On the back of your periodic table in table 5, I've also given you enthalpies of formation. So you've got 2 tables here. This is just a simpler one to work with. But again, water is a gas, water is a liquid. Be careful with hydrogen peroxide here. This is not water. And you can have sulfuric acid liquid and sulfuric acid aqueous. I didn't list them both here, but be careful. You can have it in multiple states. Make sure you select the right one. Also, I just want you to note, it's written dark, so I hope that you see it. Some substances were not on this table, so I wrote it here. Hydrogen peroxide is on your yellow sheet, but I did scribble mine in here. I do believe this is one that you will need in your classwork, so you may want to just scribble it in, negative 187.8 kilojoules per mole. It is on your yellow sheet. So let's learn how to do this. First of all, we spoke very briefly extensive versus intensive properties at the beginning of the year. It's not something we really need to concern ourselves with at this level, but extensive properties do depend on how much matter you have. Intensive properties do not. Enthalpy, like heat, mass, volume, specific heat capacity, and entropy, are extensive properties, so they do depend on how much substance you have, and that will become relevant in just a minute. I'll show you where in the formula. The other piece that's relevant in deriving our formula is that enthalpy is a state function. It depends only on the initial and final enthalpy values. The path that you take is not relevant. For example, you are in first period. When the bell rings, you will all go to third period and you will have 6 or 7 minutes to do so. Some of you will go to your locker. Some of you will run for the bathroom. Some of you will seek out your girlfriend or boyfriend so you can say hello. It doesn't matter what you do during that transition from first to third period. We only care that you started in first and you're going to third. So we don't care about the path you take, just the beginning point and the end point. And because of that, when you calculate the change in enthalpy for the reaction, as I said earlier, you can do products minus reactants. Now this not sign right here, that should be up. I guess I can't. I think it's up, down, and because I've got so much going on there, but that's like a superscript. There's a crazy formula highlighted in yellow, and it looks awful. I promise it's very easy. The change in enthalpy for the reaction is equal to the sum of, sigma means sum of, you've used it in math, correct? N, number of moles. I'll show you how to do that, and you need to take that into account because enthalpy is an extensive property. The delta H is a formation of all the products. Remember I said go PP before you run. Products minus reactants. Sum of, taking into account moles of each reactant. Delta H is a formation of reactant. So in this generic equation, lowercase letters represent coefficients and uppercase letters represent substances, elements, and or compounds. The delta H of the reaction then, products first. Coefficient times the delta H of formation of substance C plus, because it's the sum of, coefficient, delta H of formation of substance D minus reactants. Same setup. We're going to do these 3 problems together, and then you have 4 problems on your classwork to nail down. I promise you will be highly successful with this, provided that you put the practice in. And this will be the last component for quiz 4.1. It says calculate the enthalpy change for the following reactions. That is delta H for the reaction. Indicate whether the reaction is endo or exothermic and explain your choice. I'm going to do the first one out ad nauseum. You will not have to show as much work as I'm showing in number 1, but at least you'll have a really good guideline to work from. I am turning my paper sideways because these problems can get very lengthy. In number 1, I've got zinc reacting with hydrogen chloride gas. And this is another one. Hydrogen chloride can be a gas. Hydrochloric acid would be aqueous, so something to make note of. Just make sure you watch that state of matter. Zinc chloride aqueous. This is actually a reaction that you ran earlier this year when we looked at conservation of mass. My approach is I like to get the delta H of formation in kilojoules per mole of each substance before I start to really let it rip. Elements in their standard state, diatomic elements in their standard state have delta H's of formation of 0. That may or may not be listed on your table. That's something you should know. Hydrogen chloride as a gas, so I look up HCl. And again, on your sheet it shows gas and it shows aqueous. Grab the gas, and that's negative 92.307 kilojoules per mole. If I write the unit over here, I don't have to write it every single time. And then zinc chloride aqueous. On the right side, 3 up from the bottom, you'll see negative 488.19. And now I'm ready to work my problem. I've got delta H for the reaction. I'm going to write the whole setup for you. Products, 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 products go first. We've got 1 mole of zinc chloride times its delta H of formation plus, because it's the sum of, 1 mole of hydrogen gas times its delta H of formation, close, minus, this set of brackets here is the most important set coming right here. And this makes for a very long chain. I'd like to swing it straight across. One mole of zinc, that's my first reactant, its delta H of formation, plus 2 moles of HCl, its delta H of formation, and that's why I wrote it that way. The first line setup just makes a very long chain. I won't require you to write this line setup here. I just thought it might be helpful as an introductory example. Alright, so now we're ready to plug and chug away. I'm going to choo-choo this way again. My delta H for the reaction that is the change in enthalpy under standard conditions is equal to 1 mole. I'm going to continue to put that zinc chloride in because I think it might be helpful to you. And now I look for it. I've got negative 488.19 kilojoules per mole plus 1 mole. Here's your hydrogen gas. That's 0 kilojoules per mole. Close. Minus 1 mole of zinc, 0 kilojoules per mole, plus, because it's the sum of 2 moles of HCl, negative 92.307 kilojoules per mole. And I know I'm off screen. I'm going to zip it across. And once you've got everything set up, go ahead and plug it into your calculator. I'll show you how I do it. If you need to borrow a calculator, by all means, please come up and borrow one. Please make sure you return it when you are done. The way I do this in my calculator is as follows. I'm putting my calculator on the screen and trying to get the little shiny thing out of it. Go away, little shiny thing. I'm going to do that without the lamp. It appears to be better. I don't use any parentheses except the one shown in red right here. So when I plug this in my calculator, what I like to do is I've got negative 488.19. I don't need to add 0 to it, but let's say I did add 0 to it, and then I hit equals. Then I subtract open parentheses, 1 times 0 is 0, plus 2 times negative 92.307 close equals. Now in regard to sig figs, I look at the quantities that I entered in terms of kilojoules per mole. Because I am adding and subtracting, I look at the least number of I look at the least number of decimal places, not the zeros though. So for example, I've got 2 decimal places, if you will, to the 100th place. I've got 3 here, so I'm going to the 100th place. When you add or subtract, you go to the least number of decimal places, and that is negative 303.58 kilojoules. Now in regard to the units, you can see how the moles cancel and you are left in kilojoules. However, I am seeing a lot of kilojoules per mole reaction now, so that would be okay as well. I actually don't like it, but that's what I see all over the AP exam, so I'll do it. The other part of the question says indicate whether the reaction is endo or exothermic. So in this case, the reaction is exothermic because the delta H for the reaction is negative. Make sure you indicate delta H of reaction, not delta H of formation, and don't write it. And that will earn you 20 points on your quiz. Piece of cake, or so it looks. We're going to do another big example together, and then you'll be ready to rock and roll on some of your own examples. Questions here? Products minus reactants, and you'll be fine. All right, in the second example, we've got methane undergoing combustion to generate CO2 and water vapor. My approach is always to get those delta H's of formation in kilojoules per mole to get the problem going. I think it's a much better strategy. So I look, methane is negative 74.81 kilojoules per mole. Oxygen is 0. Carbon dioxide is negative 393.509. Water in the gaseous state is negative 241.818 kilojoules per mole. Now, in terms of how much work you need to show, I'm going to skip that first line that I did on the previous page. You don't need it. Start with products. 1 mole of carbon dioxide times its delta H of formation plus 2 moles of water in the gaseous state close minus. I'm going to continue with this here. 1 mole of methane, its delta H of formation, two moles of oxygen, and that's 0 kilojoules per mole. And it might be easier to just do this so you don't even have to deal with it. Again, just watch your calculator plugging here. You've got negative 393.509 plus 2 times negative 241.818. I hit equals, and then I subtract negative 74.81. In regard to my sig figs, thousandth place, 100th place, maintaining that, and I've got negative 802.34 kilojoules. Is the reaction endo or exothermic? Exo, because delta H for the reaction, that's a pretty scripted delta, is negative. Easy peasy? Okay, I'm going to have you try 3. I will reveal the answer. You do need to balance 3, and a lot of the kids were like, I can't balance it. I'm not sure why. You've got a 2-3 situation there with the iron. Work from there and you won't have any issues. So you'll try number 3, and then on the classwork, number 9, because 1 through 8 is already done. So number 9, A through D, will give you 4 examples to nail this concept down in regard to determining the change in enthalpy for a reaction. In the next lesson, we'll talk about how to calculate the change in enthalpy for a reaction where you can't use delta H's of formation, and so you need an alternative strategy. So you continue to work on number 3. You've got 3 on your Chromebooks. 3 is also on the screen. I will reveal the answer, so we've got it on the videotape. And then we'll check to see if you're right. And in the second part of the lesson, we'll determine delta H a different way.